Okay, so there are a couple of different things that look similar, but they're actually different. That sometimes gets a bit confusing. Okay, in the beginning of this subject, here we calculated the potential energy, U, and we said that the potential energy was equal to Q times the V, the potential at that point. Now, this expression basically states that U, more precisely, is the change in the potential energy of the system due to the fact that we bring an additional charge Q at the position R. This is what we mean by U of R over here. So we already have our charge distribution. The system already has a potential energy. And then we bring an additional charge Q to the position R. Of course, the potential energy of the system changes, and the change in this potential energy is given by Q times the potential at that point. This potential is created by the other charges in my system. Then, knowing this fact, we went ahead to calculate the total potential energy stored in a given system. So basically, we have to calculate all the work that we have to do in order to bring all these charges to their final positions. So we have to calculate the work done we had to do to bring them one by one to their final position. So that is what we had done over here. We don't have to do any work to bring the first charge because basically there are no other charges in the system. So the first charge can just move freely. We bring it to its final position. And then when we are bringing the second charge Q2 in its final position, well, there is already a one charge, so we have to be doing work against the force against that charge. So, and this is how much work we have to do in order to bring the charge Q2 to its final position in the presence of Q1 only. So here we only brought the first charge and then the second charge. Up to this point, we only have two charges. Although our system has n charges, n-point charges, up to this point, we only calculate the total work that we had to do to bring the first two charges. Then to bring the third charge, we have to do work against the forces created by the already present charges Q1 and Q2. But these are the potentials created by Q1 and Q2. So the work that we have to do in order to bring Q3 is nothing but Q3 times the potential created by Q1, Q2. Just like we are basically using this expression over there for each one of the charges. And then when we sum them up, to bring the charge Qi, we need to do a work that is given by Qi times Vi. But Vi here is nothing but the potential created by the charges Q1, Q2, Q3 up to Qi minus 1. Because already we have brought them, and to bring this additional charge Qi, we have to do work against all the present charges, and the total amount of work that we do is nothing but Qi times the potential created by all the present charges. And of course, we have to sum this up until we bring all the charges. It again looks like Q times V, but the Vi over here, just keep in mind that it is the potential created by the charges that we had brought before bringing Qi. But kind of this expression has this, let's say, one shortcoming that it looks as if it depends on how we bring the charges. So do we bring Q1 first, then Q2, then Q3, or do we bring Q1 first, then Q3, and then Q2? If we change the order, each one of these potentials will change. They will look different. But nevertheless, the final expression, the total energy stored in the system, will not change. It will be the same. Then we wanted to write this in such a form that it doesn't even look as if it depends on in which order we bring the charges. And to do that, we did this simple example of 3 charges, and we had seen that we can just rearrange them into a more symmetrical form. Now again, this is just like Q times the potential, the charge times the potential summed over all the charges. Now we have this one additional term 1 over 2. And this Vi prime over here is the potential created by the other charges. So we have this system of many charges. We take this Qi, we multiply Qi by the potential calculated by all the other charges in my system at the position of Qi. Now, at this, this summation doesn't make any reference to how in which order we bring the charges from infinity. So this is basically what we wanted to achieve, an expression that doesn't, the potential energy was basically the work done that, the total work that we have done to bring the charges from infinity to their final position. But this potential energy should be independent of in which order and along which path we bring them, because basically the work done in a conservative force is independent of the paths and independent of the order that we bring these charges to their final position. And this is that expression. Here, we no longer refer to the order of bringing them. So Vi prime is nothing but the potential created by all the other charges except on Qi at the position of Ri. Now, any questions up to this point?
Hocam şimdi buradaki yüklerin hepsini sonsuzdan mı alıp getirmek?
Yes.
Hani şuradan alıp getirsem ne olur?
Well, that would mean a change in the potential energy of the system. And if you want to calculate this is the total potential energy. If you want to calculate the change in the potential energy of the system, it will be still have this form, but instead of Vi prime, you would have the change in the Vi prime. Of course, that change could have been due to the change in the position of Ri prime, or due to the changes in the positions of the other particles. Now, the reason why we are bringing them from infinity is that we are assuming that the potential at infinity is zero. That is our definition of the reference point. When they are at infinitely, all the charges are infinitely separated, we say that, okay, they are not influencing each other, so there cannot be any potential energy in the system. And then when we bring them, we have to do some work. So we are increasing the potential or decreasing changing the potential energy. And this is the change in the potential energy from zero. Now we will rewrite that expression. First of all, that is for discrete charges. We can rewrite it for a continuous charge distribution. So for example, if you have a continuous charge distribution, well, a continuous charge distribution, we can always treat it as a collection of point charges by dividing it into very small bits and eventually taking the limit that each one of these small bits goes to zero. Well, here the charge will be nothing but rho at the position of that bit multiplied by its volume, and summation over all the i's, all these different bits, will be nothing but the summation of over all these possible positions. But that summation is what we call the integration. So the energy stored in a given charge distribution, we can also write it in this form. dV rho of r prime, V at r prime. Now, V at r prime is created by this charge distribution. But there's a very small catch over here, a very slight point that you have to pay attention to. You see here, Vi prime doesn't receive contribution from the charge at the position Ri. Because at the position Ri, we have the charge Qi. Here we are summing over all the other charges. That is the potential created by the other charges. But in this expression over here, let me erase the prime, V of r is d cubed r prime rho of r prime divided by r minus r prime. It can even receive contribution from the points r prime is equal to r. If the integral is finite, then there's no problem. So there's this very small difference between those two expressions. This sum over here and its continuum limit, it is just to keep in mind. We will see some consequences of this difference. Now, this is our U at the top. Well, we might prefer to express it in terms of electric field. We will see that it will be nicer. Now, how we can do that? We already know that the rho is nothing but epsilon 0 times the Laplacian of V with a minus sign. Or we can also write it as epsilon 0 times the divergence of the electric field. So instead of the charge density, we can use the electric field. We can express rho in terms of the electric field. So the potential energy stored in the system will be 1 over 2 dV. Okay, let me, instead of dV, let me use d cubed r. dV, volume element, and V, the potential. I mean, they might get confusing. So let's say d cubed r, this is our volume element, multiplied by epsilon 0, divergence of the electric field, times V. It would be nice to have the divergence of V, because that we can write in terms of the electric field. Well, but that we can still do. Divergence of electric field multiplied by V is nothing but the divergence of V multiplied by E minus the electric field multiplied by the gradient of V. Well, you see, if you take this derivative, the derivative of the product is nothing but the derivative of the second term times the first one. That is what we want. Plus the derivative of the first one multiplied by the second term. That is something we don't want, so we subtract it.
Zaten elektrik fiyatının divergent'ını alınca bir skaler fonksiyon çıkmayacak.
Okay, so?
İkisi de skaler. Nasıl böyle bir şey?
What's the question? Okay, this is a scalar. This is also a scalar. You see, this is exactly the, well, let us rewrite it in this form. The divergence of V times E is equal to the gradient of V multiplied by E plus V times the divergence of E. Derivative of a product is the derivative of the first term times the second one plus the first one times the derivative of the second one. Now, if we look at our integral over here, I have this term. So this term is equal to this one minus this one. So that's what I wrote over here. Well, what I obtained by writing it in this form is that, you see, I have a volume integral of a total divergence. But I can write it as a surface integral. That is what I will obtain. So U is equal to 1 over 2 d cubed r, the divergence of V times E, plus 1 over 2, there's also the epsilon 0, d cubed r epsilon 0 of E squared. What I did was minus the gradient of V is nothing but the electric field. So I have minus the gradient of V, which is the electric field, multiplied by the electric field, so that is electric field squared. Electric field squared. So this is over a volume. This is also over the same volume. But just keep in mind that this volume should contain all the charges in my system. Basically, because here, you see, I have this charge density, or let's go back. Here we are summing over all the charges in my system. So when I convert it into an integral, I should be integrating over a volume that contains all my charges. So this volume V contains, it can be any volume, as long as it should contain all the charges. Now this one, the first integral, I can write it as a surface integral. So this would be 1 over 2 epsilon 0 over the boundary of V d cubed r times V, the electric field, plus d cubed r over the volume, 1 over 2 epsilon 0 E squared. And this is the total potential energy stored in my system, written in terms of the electric field, a volume integral over the electric field, and a surface integral over the electric field, oops, so that's not d cubed r, and the potential. Again, V is almost completely arbitrary as long as it contains all my charges. But in particular, I can take the volume V to infinity, all the universe. So basically what I'm imagining here, I have a collection of charges over here. It doesn't go to infinity. It's not an infinite plane or an infinite wire. There's something over here. Since I have a charge only over here at infinity, the electric field would be 0, the potential would be 0. Both of these are 0 at infinity. So the surface integral will not contribute, and I am left with this term only. We take all of the universe, so the potential energy in the system is just the volume integral of, let's say, UE, d cubed r UE at the position r, where UE of r is equal to 1 over 2 epsilon 0, the electric field at the point r squared. This is some kind of energy density, such that if I take the energy density, multiply it by a very small volume, sum over all the volumes in the universe, I get the total energy of my system. So that's also why I identified this term over here, the energy density stored in the electric field. And keep in mind that this is exactly equal to d cubed r 1 over 2 rho of r v of r. These two expressions for the total energy stored in my system, they are exactly equal to each other. Of course, keep in mind that the volume in these integrals are infinite. Now, of course, at first sight, what we had done is just some mathematical manipulations, mathematical transformations, let's say, rewrote this one in terms of this one. But it also brings us a different, let's say, philosophy of looking at the energy. Where is this energy? If you look at this one, it looks as if the energy is an energy of the charges itself. We have the charges and the potentials created by the charges. So this tells me that the energy is in the charges. But if I look at over here, this expression, this tells me that no, the energy is not in the charges. The energy is stored in the electric field. The electric field has the energy. And furthermore, this is in a sense more local, because if you have an energy at a given point, then electric field at a given point, you know the energy density at that point. Here, if you know the charge density at a given point, you don't really know the energy density corresponding to that one, because you don't know the potential. To calculate the potential, you have to know all the charges. So in that sense also, this is the form we prefer, because here everything is local. Here it's not local. To determine the potential, we have to know the charges everywhere. Now, but that also brings another change of attitude, let's say. If you remember, we defined the electric field as some mathematical tool. So we put some charge over here to start with, and that charge started to feel some force. And we said, okay, and we know that that force is proportional to the charge, so let's define something that is independent of the charge, and we define the electric field just by dividing the force by the charge. It was mainly a mathematical construct we had. But now we see that that electric field, our mathematical construct, has some real physical properties like the energy. It carries energy. Just like if you throw a mass, it carries kinetic energy. The electric field itself carries energy. So in a sense, it started to have, let's say, its physical existence on its own. Now we will later on see that the electric field and with the magnetic field, it doesn't only carry energy, but it also carries momentum. So we see that the electromagnetic field, and we will see that towards the Well, I think it's next semester. We will eventually see that electromagnetic field carries both energy and momentum, just like ordinary matter. Okay, let's go back here. Now, any questions on this one? Well, you see, this change in the attitude is mainly, that is for the time being, it's still a convention, let's say, because both these expressions are practically they are same. So you can either treat the energy stored in the charges themselves or the configurations of the charges, or you can say that the energy is stored in the electric field, which are created by the charges. But once you know the electric field, you know the energy. Let's do an example. Let's imagine we have two charges, 2-point charges. This is located at the point R1, this is located at the point R2. What is the potential energy stored in this system? If we use our previous expression of, if we use just, let's say, this expression over here, we have a discrete charges. So it is just U is equal to Q1, Q2 divided by 4 pi epsilon 0, 1 over R1 minus R2. If Q1 and Q2, they are opposite charges, what will be the sign of this potential energy? Minus. So it is a negative potential energy. But now we have a problem though. Let's go back to this expression. UE is positive. The energy density of the electric field is always positive. So if you integrate it, you will get a positive energy. You cannot get a negative energy. Even if Q1 and Q2 they are of opposite charges, this electric field over here will be definitely positive. But here it is negative. Well, keep this in mind. We will be trying to resolve this problem. Let's try to use this expression to evaluate the total potential energy. Well, the electric field at the point R will be equal to, let's say that the electric field due to the charge Q1 plus the electric field due to the charge Q2, where this EI, we know what the electric field of a point charge is. This is 1 over 4 pi epsilon 0, Qi over R minus Ri cubed multiplied by R minus Ri. I is equal to 1 or 2. If you calculate E squared, this will be E1 squared R plus E2 squared R plus twice E1 multiplied by E2. So the total energy stored in the system will be 1 over 2 epsilon 0 d cubed R E1 squared plus E2 squared plus twice E1 dot E2 integrated over all of space.
Şurada biz şey yazmadık ama. 1 over 2 epsilon 0'yu.
Where?
Şu burada.
Here. No, here I have this epsilon 0. It is this over here. So this is equal to, let's say, U1 plus U2 plus U12, where this Ui is equal to 1 over 2 epsilon 0 d cubed r 1 over 4 pi epsilon 0 times qi over r minus ri squared, all of this thing squared. Well, I can just make a change of variables in this r integration. I just shift r by ri so that I don't have that ri over here, there. So ui is equal to qi squared times 1 over 2 epsilon 0 d cubed r 1 over 4 pi epsilon 0 r squared squared. I just made a change of variable. I shifted my integration variable by Ri. But you see, this is constant. So it is independent of the other charge. If you calculate U1, it only depends on Q1 squared, and, well, it doesn't depend on Q2. So it doesn't depend on the configurations I have. So when I'm calculating the changes in the potential energy, this term will just drop. Because if I move my charges, let's say, from point to point, a different point, Ui will not change. Well, constant in terms of the positions of my charges. There's no Ri dependence. They disappeared. Okay, here it looks as if it depends on the position of the ith charge, but the integral is independent of that position. So it's just constant. So this Ui is basically adding a constant to my potential energy. Which is kind of, I mean, I can always shift the potential energy by a constant. Eventually, what I care about is the changes in the potential energy as the configuration of my system changes. And these terms will not be important. Well, let me, before ignoring these terms, let me say that these constants are infinite, though. If you integrate them, d cubed r 1 over r to the 4, let's integrate them. I have dr over r squared, well, dr times r squared, times, if I integrate over the angles, that gives me 4 pi, 1 over r to the 4, r goes from 0 to infinity. This is equal to 4 pi times minus 1 over r from 0 to infinity. This is 4 pi over 0. It's infinite. But nevertheless, it is fine. It is constant. It's an infinite constant. So if the positions of my charges changes, this constant does not change. Well, the interesting part, well, these are just constants, so they are kind of, we can just ignore them. The interesting part that we cannot ignore will be this U12, which is d cubed r 1 over 2 epsilon 0, E1 at the point r, scalar product with E2 at the point r. Well, I will not evaluate this integral. And there's a evaluation in your book. If you are curious, just pick it up. And this just turns out to be 1 over 4 pi epsilon 0, Q1, Q2 divided by R1 minus R2. It is this U12 term which depends on the separation between my charges is the term that gives this energy in the discrete case. Now let's look at the other ones, U1, Ui. this was, we had defined it as d cubed r 1 over 2 epsilon 0 EI squared. You see, EI, we called EI the electric field created by a point charge in the absence of the other charge. So if you have a single point charge, this is EI is the electric field created by that charge, and this is the energy density in that electric field. If you integrate it over the whole volume, this is the energy of a point charge. Well, essentially, this is the energy that you need, this is the work that you need to do to create the point charge itself. Well, we are not creating point charges. We are already picking them up. They already exist. Since we are not creating them, that is why we can just throw them away. They do not change. That's why they are constant. This is called the self-energy. Well, too bad they are infinite, but nevertheless, it's good that we can throw them away without a second thought. Because they are constant. They do not change as our configuration changes.
Yani hocam bir tane charge olduğu yerde duruyorken bu enerji yok.
Yes and no. You see, this is just a constant potential energy. So what do you do with a constant potential energy? Well, there's nothing you can do. I mean, you cannot even measure it. Ignore it. And we can always shift our definition of the potential energy by as much as you like. Because the only thing that matters is how the potential energy changes as different parts of your system change their position. And a constant does not change. This is a constant that does not change. So you can just throw them away. Or in your definition of the potential energy, you can just assume that you define it with minus these terms. Any questions? Now let's look at an example. Classical electron radius. Well, I said yes and no to this definition, to his question, because if a system has infinite energy, then it has infinite mass, E equals mc squared. So if you imagine an electron, it cannot have infinite energy. It should not have infinite energy. So let's devise a model of the electron. Let's say that the electron is a sphere of radius r. The charge is uniformly distributed, let's say, just for simplicity, over the surface. What is the self-energy of this system? And we will set that the self-energy is equal to mass of the electron times c squared. And this will tell us what the radius of the electron is. Now, we first need to evaluate the self-energy of the electron. Once we evaluate it, and it will be a function of the radius of the electron, we equate it to the rest mass energy of the electron. So that will tell us what at least the classical radius of the electron is. What's the electric field of this configuration? We have a spherical shell. There is a charge uniformly distributed.
Phys331
So it is 0 if R is less than RE, and R is larger than RE. QE over 4 pi epsilon 0 in the radial direction divided by R squared. So the self-energy of the electron, 1 over 2 epsilon 0, T cubed R, the electric field squared, which is equal to 1 over 2 epsilon 0, dr times R squared starting from the radius of the electron up to infinity, times sine theta, d theta, d phi. Phi goes from 0 to 2 pi, theta goes from 0 to pi. We are integrating over all of space. Well, E squared is QE over 4 pi epsilon 0 squared 1 over R to the 4. So this will be equal to 1 over 32 pi squared epsilon 0 charge of the electron squared. Well, the phi integral will just give me 2 pi. The theta integral, if you evaluated it, will give me a 2. So that will make a 4 pi from RE to infinity dr over R squared. Well, the pi's cancel. The 4's I can cancel with 2. I have 2/3 QE squared over pi. And the integral is 1 over R ranging from the radius of the electron up to infinity. And I also have an epsilon 0. So this is equal to twice the charge of the electron squared divided by 3 pi epsilon 0, the radius of the electron. This is the self-energy of the electron. And if we equate it to the rest mass energy of the electron, we obtain the radius of the electron, the classical radius. At least in this model, we assume that all of the mass of the electron is due to its self-energy, due to the electrostatic energy. It's just a model, which unfortunately doesn't work. Well, you see, there are a couple of problems. The most serious problem with this one is if you have this sphere, now the electron also has this angular momentum that we call the spin. Well, the easiest thing in this model will be just assume that this sphere is rotating around itself to create the spin of the electron. Well, you know the radius of the electron. You know the mass of the electron. So you can determine what should be its angular velocity. We already know its spin. We measure its spin. So we know its angular velocity. If you multiply the angular velocity of the electron with its radius to obtain the speed on the surface of the electron, it turns out to be larger than the speed of light. So that's basically why we don't like this model. Well, the radius of, as far as we know, the electron is a point object. It doesn't have a radius. Well, you see, the electron that we know now doesn't have a radius. It's a point. But this was one of the old models, let's say. Once you do, the Maxwell's equations, they were developed in the 1800s. So once you discover the electron, you don't know what it is. You don't know about quantum mechanics yet. So then there is this question. There was this question of the self-energy. Well, you see, for a point object, this self-energy diverges. So how can we make sense out of it? So this model basically stated that, okay, the electron is not a point object. There are no point charges, but the electron is a sphere. Well, also the particles have mass. Well, why do objects have mass? That's another problem that we would like to understand. Why is there something called mass? Well, this model kind of tried to give answer to both of these questions. One, what do we do with the infinite self-energies of point objects? Second, where does the mass come from? So in this picture, the electron was a sphere, and the mass of the electron was only due to, you see, what we call mass is basically the minimum energy that an object can have. That's what we call the mass. Well, this object definitely has its self-energy. If we assume it to be a sphere of some finite size, then the self-energy of this object is finite. So the most natural choice would be just to equate the self-energy of this object with its minimum energy, which we call the mass. That would allow us to determine the mass of an electron. So basically, it answered both questions. First of all, the self-energy of the electron was not divergent. It was a finite number. Secondly, it also told us where the mass comes from. The mass is nothing but the energy stored in the electrostatic electric field of the electron. It would have been really nice if it had worked, but future discoveries told us that it cannot be true. It was a nice, elegant idea, which unfortunately didn't work.
Peki bunu buldukları zaman hani ne bileyim ortama falan bağlı gözüküyor yani eksinomuz zero falan içinde. Ama o biraz soru işareti yaratmamıştı. Sonuçta elektronun işte çapı ortamında bir
Well, epsilon zero is the epsilon zero in vacuum. Here it's not the epsilon, it's epsilon zero that appears. Secondly, the mass of the electron, I mean, you can define a mass of the electron in medium, which will be different than its mass in vacuum. Effectively. Now, we will study in medium effects later on. So in medium effects is basically an averaging. On the average, an electron can look larger or smaller in medium. Other questions? Well, we see all the consequences of the existence of the electron. Observationally, it exists. Well, that means that we would have to change a lot. It's highly unlikely. Okay, so that's it for today. See you on Tuesday.